Good morning, students. Okay, today we are going to learn a new topic, how this resistance of the system of resistors. So in the last class we learned on resistance, and there is a little difference between the resistors and resistance. And today we are going to learn some more about how they are connected. Resistors, when they are connected in different types, different ways, they perform differently. So today we are going to learn how these resistors are going to get connected, how they are going to get connected. Okay, uh, and what are resistors actually? So first of all, we learn what are resistors. What is resistance? Resistance, the last class we learned, it is a property of any object to resist the flow of current, right? So, for example, in the last class we learned that if there is lots of electrons or in a metal or any kind of an object, it resists more, right? So resistance is it talks about the property of how the flow of current is getting resist or stopped. What are resistors? Resistors are the object that really resists the flow of current. Even you can see these kind of resistor. I have drawn a diagram like this is one of these resistor. There are two different types of resistors. Some are wire bond resistors, another are carbon resistor. This is somewhat like carbon resistors, and you can see some colored lines are also given on the small resistors. You can see these kind of resistors on inside the circuit of TV or refrigerators or somewhere electrical appliance. You can see these kind of small things inside that, and these are wire bond. It is actually the lots of wires are wounded on the metal wires. These are wire bond resistors. Why these resistors? Why we need these resistors? For example, it is actually the main thing to prevent the huge amount of current passes through the circuit. For example, if you have a TV or refrigerators, these resistors are inside your TV or refrigerators. Most of your electrical appliance, you can see these resistors. Suppose a huge amount of current comes in through that uh, through the current or your TV or refrigerators, this resistors sometimes it stops the huge amount of current, because even they have some amount of potential difference. That means they can hold up most amount of current. They can stop most amount of current. They can hold up most of the current with themselves. Even some resistors are colored. You can see this colored. Why this color? This colors also talks about how much potential difference they have, how much potential difference they can hold up. Okay, on and show that only they have a different colors are given on the resistors, and these resistors are available even in the markets. Suppose if you have 100 ohms of resistance, and that is what you need, add 5 ohms of resistance or 60 ohms of resistance, they are easily available in the market. But suppose if you want 99 ohm of resistor, you can't get it. So what we do normally, so we try to connect 2-3 resistors together. For example, 50 resistors at one place. First 50 ohm, another is, then we connect with 20 ohm, 220 ohms, then 5 ohms or 2 ohms. So totally 99 ohms of current we try to get it. Will you all understand that? So we used to connect these resistors either series or parallel. So how these are getting connected? Either by series or by parallel. So first we are going to talk about how these resistors are connected in series. For example, these are the 3 resistors. are connected in series. Series means one after another, just like that. For example, this is a circuit diagram, a positive and negative battery, and connected with a key, and ammeter is there. You know why this ammeter is connected, right? To see the current, how much flow of current. And voltmeter was also there to see the potential difference. Okay, and also we have three resistors, R1, R2 and R3. Okay, so what happened when we switch on the current flows through this. For example, in this series connected, and the current is flowing from X to Y. If it is moving from this direction, current, so I made this in a big in a big size, so I made it like this. You can see here current is flowing in this direction, and these are the three resistors, right? And the current which is flowing in this resistors are same type of current. There is no difference in the current, same amount of current which is flowing from R1, R2 and R3. But the potential difference, you know what is potential difference? The charge which is flowing from R1 to R3, R2 to R3, right? They are totally different, right? Because they don't have the same type of charges, because here some of these current are resisted here, so they have some potential difference. And here when they moving, charges are moving here, because another resistance are there, so it resists some of the current, right? Charges. So here the potential difference is totally different. So I can say that current through each resistors are same. The first one is current through each resistors are same type of current, but the potential difference across each resistors are totally different. So what is the potential difference here? It is V1, and here it is V2, and here it is V3. So what could be the potential difference across R1? So only if I talk about R1, what is the potential difference only for R1? So according to Ohm's law, you know what is the Ohm's law? Ohm's law is equal to V is equal to IR. So if I try to write Ohm's law, according to Ohm's law, it is V1, that is potential difference across R1 is V1 is equal to IR1. And potential difference according to R2 is IR2. And potential difference across R3 is V3, that is IR3. So if I find the total potential difference of everything is V is equal to V1 plus V2 plus V3. So if I am taking all the potential difference, V1 plus V2 plus V3, all the potential difference. So IR, that means V is equal to what? V is equal to IR. So I am writing it as IR equivalent. What is this IR equivalent? The equivalent resistance of the circuit, the whole circuit, the equivalent resistance of the whole circuit. In other words, there is the same amount of current which is flowing in that, through that, and there are, you can see here, a different potential difference you can see from R1 or R2 and R3, and that is IR equivalent. That means the net resistance of the circuit, the net resistance of the circuit, IR equivalent is equal to IR1 plus IR2. For V3 it is IR3. So if I write like this, if I take out I common, so I get I R1 plus R2 plus R3. So both I from both sides are getting cancelled. So I find resistance, the equivalent resistance is equal to R1 plus R2 plus R3. This is what the resistors, this is what happened when the resistors are connected in the series. If you have a book, you turn to page 212, and you can see here also given, and here they have not given R equivalent, they have given RS. S talks about the series. So we conclude that several resistors are joined in series. The resistance of the combination Rs, that is equal the sum of their individual resistance. Rs equals the sum of the individual resistance R1 plus R2 plus R3, thus greater than any individual resistance. Okay, that is what we are learning here. So R equivalent is equal to R1 plus R2 plus R3. And next we move on to the resistors connected in parallel. How they are connected? For example, and this is the circuit diagram, you can look at it. Same battery or a cell with a key ammeter is there and a voltmeter, and these here you can see they are connected not in the series, parallel. So I made a little bigger one. This is their parallel current which is moving here, and this current is distributed to three different resistors, not like series. You can see same amount of current is distributed, or same amount of current which is passing in R1, R2 and R3. But here the current which is moving in the parallel, they are distributing the current into for R1 or R2 or R3. For example, I can say that if a big pipe, the water is traveling, a 10 liter of water which is traveling in a big pipe, and there are some branch pipes are comes in this big pipe connected with the big pipe. So what happened, there is equal amount of water is distributed, am I right? For example, if 10 liters of water which is coming in this big pipe, they will be distributed equally in three different of small pipes, like 3.5 or 3.5 or 3.5 or something. So the water will be distributed equally. So that is what happened here. The same amount of there won't be a same amount of current. You can see here the current through each resistors are different. So if the current which is coming here and that will be equally distributed to R1 and R2 and R3. So the current through each resistors are different, and the potential difference across each resistors are same. So but the potential difference which is takes place here is V1, V2, V3, and these three are going to be same. There is no V1 or there is no V2 or there is no V3. All the potential difference are going to be the same. That is what here they are talking about. The potential difference across each resistors are same. So the total current flowing through the circuit is I, right? So I can distribute the current into I1 plus I2 plus I3. So according to the Ohm's law, we can write it as V is equal to I R equivalent. That means equal amount of resistance, right? Each resistors are same. So I can write V is equal to IR. So I is equal to V by R. So I can write it like this: V by R equivalent is equal to V by R1 plus V by R2 plus V by R3. So if I write like this, 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So this is what we can talk about resistors connected in the parallel. So this is what actually connected in our home. So for example, if we are getting 260 volt of a current which is coming to a home, this current is distributed for different purposes, right? For example, which appliance which is used in our home or using more current, that will be taken more current, and the one for fan or a bulb and all, they take little amount of current. So they distribute the current according to the work which is the working appliance which is used in our home, right? So this is what we can say, the resistors connected in parallel. Heating effect of current. What is actually the heating effect of current? However, you can look at it. So whenever a circuit, the current is flowing in a circuit, definitely there will heat will be generates always. if you see that when I amount of current which is moving inside the circuit, think that definitely when it passes through this resistance, definitely there is some amount of heat will be generated. Okay, that's what happening. So I flows through R. I is flowing, that means the current which is flowing through the R. There is some amount of work done in moving a charge Q through the potential difference. I want you to remind you one thing. When we learn on potential difference, I gave you an example, Rahul and John. So Rahul is bringing a charge from infinity to one place, any one place like A. So what he is doing some work on bringing one charge to from here to here, right? That's what we learned. Remember, if you have not even seen that first video, I want you to look at once again so that you will understand the potential difference, what will happen. So some amount of charge they are bringing from infinity to one place A, right? And not only this, so not only they are bringing the charge, so Q, and that is what actually the potential difference, right? So the work has been done. So work done on moving a charge Q through potential difference V is nothing but QV, right? QV. QV is what? That is what the work done. So work done is equal to QV. That means the work done in moving a charge Q through a potential difference V. So let's learn one more thing. So the power input to the circuit P. Okay, if some amount of power which is moving in a circuit, right? So the power input is nothing but work done upon time. We know already that power is equal to work upon time. In a particular time, how much work you can do. That is what actually the power, right? So we know W now. So substitute this W in this equation. P is equal to W by T. What we will get? Yeah, we'll get this. P is equal to QV by T, right? So P is equal to W by T. It was given. So we are substituting that QV on there. So it comes QV by T, right? So as we know already that I is equal to Q by T. Where we learn this I is equal to Q by T? I want you to turn to your book and you find it out. I is equal to Q by T. Yes, the amount of current which is equal to the charge upon time, right? So I is equal to, substitute this here in this equation. So we get P is equal to, so Q by T. Here we are substituting as I. So it comes VI. So P is equal to VI. So this much power is supplied to the circuit. So which circuit? Yes, here in this circuit. So this much power which is supplied. So the energy supplied to the circuit is P into time. So how much power on a particular time, if the energy which is supplied in a circuit, that is what the H is nothing but energy which is supplied in the circuit is nothing but the power into time. So P we already know it's VI, so substitute as VI here into T, so we get VIT, and this is nothing but this much amount of heat is dissipated in the resistor. So as we know that here, so when the some amount of electricity which is passing through this from here X to Y, right, some amount, this power, some amount of heat which is produced on the resistor, and how much it is VIT, this much of heat which is produced or dissipated in the resistor. I hope you all understand this. So from Ohm's law, what we are learning, V is equal to IR. This is what Ohm's law. So can you substitute everything here? Yes. So H is equal to VIT, right? So substitute V is equal to IR in H, sorry, V. So what we get? We get IR IT. Am I right? H is equal to VIT. So that is what we got it here. So H is equal to, here for V we are substituting this. So we get IR IT, right? So that is what I have written here. So two i's are here. So I into I, so it becomes I square RT. So I square RT. This is what's said to be a Joule's law of heating. Okay, Joule's law of heating. What is Joule's law of heating? If you can see this properly, you can understand it. It is the squares of current for a given resistance, right? We see the squares of current of the given resistance. The heat produced in a resistor is directly proportional to how much heat which is produced on this resistance in this how much heat which is produced on this resistance. That is nothing but it's directly proportional to squares of the current, resistance for the given current, and the time for which the current flows through the resistor. Okay, let me explain this in a different way. So I can say that squares of the current for the given resistors. And think in that way, if a more amount of current which is passing in a circuit, normally what will happen? Heat will be generated. Am I right? So the squares of the current, that means if more amount of current, more amount of heat energy. That is what this line talks about. A resistance for a given current. If think of that, we have one resistance. So it depends upon the how much resistance we have on a circuit. If you have two or three, so as I told you, one resistant will be there, it means it resists some amount of current. If one amount of resistance, one resistant is there, it resists more current, right? If two resistance are there, that means it resists even more. So that is what there. If resistance is there, definitely it is directly proportional to the heat energy. I hope you are understanding it. And another very important thing, the time for which the current flows through the circuit. If it takes more time, for example, the current is flowing in a circuit for a long amount of time. For example, if the fan is running for the whole day, then definitely for the 2 hours, 1 hour means little amount of heat, 2 hours even more amount of heat, 5 hours more amount of heat. So it directly proportional to the time also. That's what I want to tell you. The first thing is squares of the current. If more number of current, more number of heat energy. Resistance, if it is there, definitely heat energy will be there. Time for which the current flows through the resistor, yes, if more amount of time the current is flowing in a circuit, definitely heat energy will be produced. So this is what talks about Joule's law of heating, right? So let's learn about the practical application. What are the practical applications of these heating effects of electric current? You can turn to page 218. There you will look at it, the practical applications of heating effects of electric current. And mainly through this heating effect of electric current, we are still using iron box in our home, electric toasters are there, electric ovens are there, electric kettles are there, right? It's all one of the applications which is used for heating effect of electric current. Another thing is, you can see, another thing is we are using some bulb, right? 60-watt bulb or something, and mainly there is a tungsten filament which will be there, right? The strong metal with a high melting point such as tungsten filament is used inside that. So what happens when it glows? That means it burns. That means when it burns, it gives lots of heat energy as well as light energy. So that is also we are still using, and one of the applications of heating effects of electric current. Another thing is fuse. We still use fuse nowadays. That fuse is replaced into MCBs. But what is the actual procedure in the fuse? Fuse are made up of some special wires which is connected on the series. What happens for the domestic purpose? If a huge amount of current which is comes suddenly to the home, that wire, the fuse wire, the fuse wire is get break up or breaks, and it stops the amount of current to come inside our home. So that is also, and this is what our last topic, electric power. Okay, what is electric power? Electric power talks about the rate at which energy is dissipated or consumed in an electric circuit. You can look at this in your book. So this electric power is nothing but a rate at which electric energy is dissipated or consumed in an electric circuit. Okay, so that means the power, it talks about power. So I write it denoted by the letter called power, and the SI unit of power is watt, which is given as W, capital W, right? What is the power consumed? Power consumed by a device carrying 1 ampere of current when operated at the potential difference of 1 volt. That is, just before we learned what is P, that is what is power. I want you to remind you once again, power is nothing but VI. So the amount of power which is supplied inside the circuit. Okay, so that means the energy which is consumed in an electric circuit, right? That is nothing but P is equal to VI. So what is the SI unit? How we can write that? Power can be written as watt. So 1 watt is equal to V can be written as 1 volt, so potential difference, and I can be written as 1 ampere. So we can write it as 1 volt is equal to 1 volt into 1 ampere. 1 ampere of current which is in a potential 1 volt of potential difference, which is talks about 1 watt. In other words, we can say that a device that carries 1 ampere of current when operated at potential difference of 1 volt, and that is called a watt. In other words, the power, 1 watt. Okay, according to Ohm's law, as we know that Ohm's law, V is equal to IR. So this is what Ohm's law. So same equation, that is P is equal to VR, can be written as two formulas. How we can write that? P is equal to VI. This is what the formula. So according to Ohm's law, V is equal to IR. So we can substitute V here in this V. So we can write it as P is equal to IR, right, and I. So it can be written as I square R. So P is equal to I square R. So it can be written in this way. So there is another way of writing that. So here P is equal to VI. So V we have substituted now. Even for I also we can substitute. So here I is equal to what? V by R, right? So V by R. So we substitute. Right, already I is here, and it is going to be substituted here in this I. So P is equal to V I. So I have substituted V by R here. So it comes P is equal to V square by R, right? So in this electric power, we have three formulas. One is P is equal to VI, P is equal to V square by R, P is equal to I square R. So these are the three formulas talks about electric power. Hope you all understand this topic, student. And I want this is the end of this chapter, and we finish this chapter. Hope you all understand this chapter properly. And if you have any doubt, please let me know and send some message so that I can clear your doubts. and after this I'm going to prepare a video on the numericals part, because that is very important in this chapter. So we'll do one by one all these numericals in this chapter, and this is the end of chapter 12, and complete all your works which is given, and have a nice day. Thank you.